Today we're looking at exercise 4A on rectangular hyperbolas. Now this is actually a concept we've looked at in the past, though albeit in a different name. So in the past we looked at the idea of why x over 0, or anything over 0 I should say, does not equal to 0, infinity or negative infinity, but rather it being an undefined value. So if we have our value, let's say we have 1, let's do something easier actually. Let's say I got 10 over x. All I'm doing is that I'm substituting some value of x every time. So let's say if I have 10 over 100. Put that in the calculator and you know you get something like 0.1. Well, not something like, but you get 0.1. If I slowly decrease this value, 10 over 10 becomes 1. If I decrease that denominator again, closer to 1, I get 10. If I keep going, you'll know that I've put 0.1 on the bottom, which is still a positive value, but is greater than, is closer to 0. That becomes 100, and so on. What's happening is that as I get closer to the value of 0 from the positive side, we end up with an extremely positive value. So I'm going to go ahead and show this, and you can see that as I go closer towards the value of x equals 0, or in other words, the limit as x approaches 0 from the positive side, we end up with the y value being, well, infinity, right? Theoretically, as I keep decreasing my value towards closer and closer to 0, my value of y should theoretically get to infinity. But we discussed why that's not the case. We know that if I was to apply, and we're applying understanding of limits from our last topic. So if I apply my limits, as x approaches 0 from the negative side, you'll see something slightly different occur. If I say 10 over negative 100, you know that gives us negative 0.1. If I continue to provide a denominator that is closer to 0, but is slightly less negative, we end up with negative 1. Keep going, and I get 10 over negative 1 gives me negative 10. And you'll see a trend that as I keep increasing, so decreasing my denominator, my value of 10 over, let's say, negative 0.1 becomes more and more negative. So that becomes negative 100. As I get closer to the value of x equals 0 from the negative end, we have a function that actually looks something like this. Now, it's not possible for a value, let's say 10 over 0, it's not possible for that value to have two different answers. Right, so we say it's undefined. What's happening is that there's an asymptote. You remember the term asymptote from our previous topics? An asymptote at where x equals to 0. Because we know that if I have, for example, 10 over x, x cannot equal to 0. If x equals to 0, then we've got a value that's not defined and therefore doesn't exist. So this is what we call a vertical asymptote, because it's vertical. And you can probably guess by the name, it's quite intuitive. This is what we call a horizontal asymptote. It's a horizontal asymptote where y does not equal to 0, or rather, where y does equal to 0. So y cannot equal to 0. That's why we have that asymptote. Y cannot equal to 0. Now the reason why y can't equal to 0 is because, well, if I put in whatever value of x, there's no way that the output, or my y value, is going to equal to a value of 0. I could put in x equals to a really small number, let's say x equals to 1, and I get 10 over 1, so an actual value besides 0. I could put a positive a million, negative a million, whatever it is, we still end up with a value that's greater or less than 0. And so typically with our rectangular hyperbolas, we have two asymptotes. Continuing on from there, we're going to look over here and see that we've got our hyperbola function. You'll see that it's also got a fraction. We'll keep that in mind as we move forward. So over here, we've got a over x minus h plus k. That's the shape of our function, or the function equation of our function family, sorry. Or we have that, which is the same thing, but we've changed it into having a negative indice. I'm not going to fill in the table. You're more than welcome to do so, but it shows the same idea that we have before, where if I have a certain value, I can change the value of x, and you can see that my y value changes accordingly in that shape. Now over here, we'll apply understanding of transformations in order to make sure we actually understand how to sketch these graphs. So for dilations, you guys know in the past, dilation affects how wide, skinny, whatever our graph looks like. Now over here, you'll see our standard line, which is going to be this red line. This red line here, red dotted line, symbolizes the standard line, or the standard line of x, 1 over x, sorry. And you'll see that from this end, the positive end, it looks like that, and the negative end, it looks like that. When I increase the value of the numerator, so instead of being 1 over x and 2 over x, it becoming 2 over x, we end up with this yellow line here, which shows that the values of y are all increased. They're all doubled. So they're all increased, and you can see that the function will continue. So if I was to continue the straight line of y equals to 1 over x versus the y equals to 2 over x, you can see that the lines themselves are increased. Whereas obviously on the other end, if I was to have 1 over 3x, which means I've got a denominator which is larger than before, I end up with values that are smaller, so my y values are smaller and closer to my x-axis. Reflections are quite straightforward. Instead of my function being like this being my y equals to 1 over x, if I chuck a negative in the front, my whole function flips, and I end up with it flipping along this line here. It flips this way, or you could technically say flipping this way as well, but let's keep it to one side. So we can flip it that way, and we end up with our function going this way and this way. Most importantly, our asymptotes don't change in this circumstance in particular. And finally, for translations, which is our most common type of transformation for this type of graph, we're focusing on where our function shifts. Now, it's pretty much the same as our cubic functions or our parabolas, if you remember those kinds of translations there. So we're going to look over here and say that, well, the value on the right-hand side, the positive value means it shifts up, negative value means it shifts down. Something you guys are already aware of. Now, treat this as if it's inside the bracket, just like you guys did with parabolas. Right now, it's a -1, so you do the opposite, because it's in the fraction. We do the opposite, and we shift 1 to the right. You'll see that as I shifted 1 unit to the right, then therefore, my asymptote shifts 1 unit to the right as well. As I shift 3 units in the positive direction of the y-axis, my asymptote does the same. Let's put this into practice with an equation over here. So it says sketch the following, where we've got y equals to 4 over x minus 1 plus 2. Right off the bat, I know that my asymptote is going to be at +2, where y equals to +2. I know that because of the extra +2 in the end. So my asymptote is going to be about there. I'm going to draw a dotted line to symbolize that asymptote there. And you can see I'm going to label that as y equals to 2. Next thing I know that my asymptote, my vertical asymptote, is going to be at where x is going to be +1. Remember, it's inside the fraction. We treat it like it's inside the bracket for when we did our parabolas. I'm going to go ahead and draw that dotted line there as well. And that's going to be my x equals to +1. Now I'm going to go ahead and draw, or plot actually, some points that I know are going to be pretty good. I'm going to substitute y equals to 5. And the reason is because if I put y equals to 5 here, that gives me 4 over 5 minus 1, which is 4. So 4 over 4, which is 1, plus 2 gives me 3, which gives me a value of 5, 3, bam. Just so I have something to anchor my point against. I'm going to do the same thing on the negative end. Let's say I put -3, x equals to -3. So that way I get 4 over -3 minus 1, which is 4 over -4. If I'm going to write that out, I'll write it like this. -3, oops, my apologies for that. 4 over -3 minus 1, and then we have the +2, which gives us a value of +1, so we have that there. And just based off that, I'm going to go ahead and fill in the gaps, and we end up with a function that looks like this. Now, your function should not actually curl back up. That would be incorrect. It should theoretically get closer and closer and closer to the asymptote without actually touching it. Okay? So it should look something like, oops, that's not correct. Looks something like this. There we go. If the question asks you to actually plot or find the x-axis intercepts, you'll have to do so. Otherwise, something like this will be fine. Let me know if you have any questions. Best of luck.